Okay, hello everyone. Good morning. So I would like to start with the thing 2 questions. This is from chapter 3. Specifically, the um, the thermal expansion included here. And if you remember that we are going to use what we call the compatibility equation. Okay, try to look at the questions, and I think they are all the informations they are already provided. So yeah, I think you can just look at the informations like the E, the area, the length, and the thermal expansion itself. Okay, so that will be in the calculation. So both 1 and 2, the materials 1, materials 2, they have each E and each thermal expansion that you need to compute each one of them. Okay. And the first question is asking the axial stresses. If there are some delta temperature, if you increase the temperature, and then it is also asking you where the node B will be moved. Okay. Is it going to the left or going to the right? The B is here in the middle. So to know which way to go, then we need to look the calculation on each materials, the A and it's the 1 and 2. Okay. So try first. I think also if you look at on the picture, on the figure, I think there are no external forces, right? There are no external forces. So I think you can directly say the equilibrium, you can write the equilibrium already. And for the assumption, if you look at the picture, you see the assumption that the B is going to the right? But this is assumption. Okay? You can make another assumption that B going to the left in your calculations, okay? And you will see the truth or the correct movement in your calculations, whether it's the positive sign or negative sign. Okay? If it is opposite, then like for example, if it's going to the right in the picture, but your calculation is negative, means that it's going to the opposite side. Okay. So all the informations E1, A1, L1, E2, L2, A2, all in the given problems. Also the alpha 1, alpha 2. and both will be increased in temperature by 15 degrees of Celsius. Okay, the formula that you need is, I think you can take the elongations or the displacement is equal to F L A E, right? But now we need to add with the thermal expansion. So alpha L delta T, right? And since we have two materials, so we will have E1 and E2, right? Okay. But we need to connect both materials 1 and 2, right? If you are not getting or you're not getting the connections, it will be difficult to solve. So you need to at least you need to make one assumption what will happen in this type of problem. So if you see the picture, let me move picture here. If you see the picture, so the question is already mentioned that the two-segment rod is attached to rigid supports. So rigid support, so that's the key. So this A, let's say the rigid support is like a wall. So A and C, which means that if this is going to be expanded, this rod going to be expanded, because of we have this rigid, then when it's going to expand, it's actually still at the same length, right? the wall or the rigid support is still there, right? So actually what happened is the elongations for 1 and 2, if you, for example, if we take the E1 is make it elongated, the 2 will be reduced, right? So if this is increased, this 1 is going to decrease. So the total displacement for these two materials will be 0. So that's one assumption. So if we can take that assumption, then we can rewrite the formula, okay, and then we can relate 1 and 2, okay, from those assumptions. Okay, so that E1 plus E2 is 0. So let's just write the assumption. So based on the rigid support, so E1 plus E2 is 0. Okay. And then if you would like to draw more clearly for, let's say we are going to cut right in the middle, so we have these two material cut and we take the middle part, so we are going to see at least the internal force for F1, right? And then we have the reactions from these materials to F2, okay? And this is B. And from here, we can just say that, okay, the internal force needs to be cancel each other, right? So F1 is equal to F2, or we can say it's just F. So when we put into our equations, we can cancel this F. Okay. So we put our formula both into E1 and E2. So F1, L1 over A1, E1, and then plus alpha 1, L1, delta T1, plus F2, L2, A2, E2, plus alpha 2, L2, delta T2. And it needs to be equal to 0. And since we need to know, the question is asking the sigma 1, sigma 2, right? So let me just rewrite this F1A1 and F2A2. I think we can write sigma if you would like, but let me just write and calculate the F first, okay? Okay, let me write here F1, L1 is 2 meter, A1 is 1/250 millimeter squared. Oh, I think we need to exchange to millimeter. So let me write 2000 millimeter. And then E1 is 200 GPa. Let me write in MPa, so Newton over millimeter squared. And then plus alpha 1 is 13. Okay. And then L1. Oh yeah, the same. I think we can just write 2 meter. Delta T is, or maybe let me write with millimeter to make it equal. Delta T is 15 degrees Celsius. Okay. and plus F2, or let me write F1 and F2 as just F. L2 is 1.5, so 1500 millimeter. A2 is 2322 millimeters squared. B2 is 70 GPa, and I will write in terms of MPa plus the alpha 2. And 15 degrees Celsius. It's equal to 0. I think we can take this 2000 multiply with 15, multiply with 13, divide with, so this will be 0.39. Zero 0.5265, so plus 0.59. So we can write this is F is equal this is going to be, I think it's safe, just, yeah, I just realized we can maybe simplify it first. I think maybe easier. But either way, it should be the same result. This is the L1, A1, E1 plus L2. So this will be negative 0.95 over plus so 1.7 228. So 0. Okay, this will be negative 53196 Newton or kilonewton. Okay, so this is F, and then we from that we get sigma 1 sigma 2, right? This is F over A1, this is F over A2. So this will be negative 42.55 MPa. This will be 22.9 MPa. So the negative means that the stress is incompressive. So both incompressive. So this is relative to the wall, to the rigid support, that it's going to affect as a compressive stress. Okay. Okay, we can take the displacement, this UB, as a assumption that we need to assume that the material 1 will be elongated. Okay, so assume that 1 is elongated, mean it's increasing. Okay. So in our calculations, then E1 is, we include again all the necessary so that will be on our answer. Okay. So we take the and we need to include the negative from here, okay, inside the F. So we need to be consistent from the very first introduction, and in the process also we need to be consistent. So put all the informations. Let me just directly count. So 53196 multiply and then plus so this one is 8 millimeter per Newton, and multiply with the F is and plus the 13 . And this should be negative 0.8155 millimeter. So since this is negative, and in the picture we assume it's going to the right, then we can say that node B, so this is UB. So node B is moving to the left. Hmm? If you choose the B to the left, okay, that way, which means that the the one will be in a reduced, right? The material 2 will be increased, right? So you need to choose material 2 to be increased. Okay. So the E1, instead of E1, you take E2 for that one. Okay, I think should be equal.
It should be positive.
Yes. Right. Okay, another type of questions that we might see is this one here. It's a little bit combination both from the temperature, the thermal expansion, and some of the geometric observations, because we are going to see some angle. And then remember that you need to have assumption, and most assumptions for like if we have like a change in angles, mostly in mechanics, we are going to assume that the angle will be very small, okay? Which means that we are going to approach the angle within the tangent, So the angle itself will be equal to the tangent. So that we are going to play with some geometry, okay? Usually a triangle. If you see here, it's going to be making a triangle because it's going to ask the small angle. So let's read for a while. Maybe I'm not completing all the solutions for this one. But let's say we have this steel rods. Okay, steel rods. This has two identical steel rods. The area is already given, E already given, so we don't need to calculate the area. And then the thermal expansion also given for the steel rods. And then rigid being AC. Okay, so if you prefer rigid, every time you saw the rigid in the questions, it means that we are going to mostly ignore most of the information from that beam. Okay, so we are going to focus on the rod 1 here and rod 2. Okay, we have the height, we have the information given. Okay, and then it's joined by or supported by the smooth beam at B. Smooth beam here, and by the picture you see that it's slightly inclined, which means that it can move. Okay, it can move, and this rod can have some movement through that B. Okay, so the beam AC can incline, okay, based on the support. Okay, the B support. And then the nuts at A and C are initially tightened just enough to remove the slack, leaving the two rods stress-free. So we are not really worried about the stresses there because it says it's stress-free, but that's also another assumption. Okay, the first question, determine the axial stress induced in rods 1 and 2 if the temperature of both rods is decreased by 50 degrees Celsius. Decrease means it's going to be negative. And then determine the small angle through which the beam AC will rotate due to this temperature change. So when the temperature change, the beam will incline because it will rotate, and you need to observe how small the angle will be. Of course, if you want to start with the equilibrium, you can start with equilibrium. Okay, you can state the internal force if you want. You can state that there will be equilibrium, and I think you are going to use moments. Okay? You can take the moments at B, okay, to know the internal force at 1 and 2. Okay. I think let me help you to take the free body diagram. And let's say this is the beam, so beam AC, okay, and then let's say B is on the middle here, or near the C, right? So B, and then we can take the internal force. This is F1. Let's say this is also F2. And then at B, we have a smooth pin that can rotate, right? So we have pin that is affected by two forces, that's By and let's say Bx. Okay. Okay. The first one, I think we can analyze the F1 here and F2. So we can take the moment here. We can take the moment with respect. So we can take this moment and take the moment here, and we can know the relations between F1 and F2. That's, I think, very first step that we can take. So take the sigma moment at B, that is equal 0. Okay. So this will be 200. This is 200 millimeter. This is 80 millimeter. Okay. So let's say this is positive like that. Okay. So 200 millimeter F1, and then minus F2, 80 millimeter, equal to 0. So F2 is 200 over 80 F1, or this is 2.5, right? Or we can say the F2 is 2.5 F1. Okay, now the first step is done, and mostly for all the mechanics, we start with the equilibrium. Okay? And then, because we are going to see some elongation or maybe some displacement, this formula will be very essential. And because we have the thermal expansions, then we need to add with the alpha, and then L, and then delta T, and the total elongations. Okay, now to take the E, okay, because we have 1 and 2, both will have E, right? Again, we need to take the compatibility equations. Okay, it means that we need to relate E1 and E2 in some way that is going to explain all the information here. So based on what we have, because we are going to find out later the angle. So perhaps we can start with looking at the geometry of the angle. Perhaps we take the descriptions. Okay, so if we look here, okay, we can take one assumption. Okay? If this 1 is going to be here, which means that this will be increasing some E1, right? When this increasing, this will be decreasing, right? This is E2. So we can take that as our basis. So we can take that. Let me just write as a triangle here, and then write down. Okay, let's say that is maybe going to be left. So this will be E1, and this will be negative E2. And we have some angle theta, right? And then, or perhaps we are going to have more downside here, I think here, everything better. And now we take, this is 200 millimeter. And this is 80 millimeter. Okay. Now, mostly what you need to do is observe this geometric and use the triangle relations. So we can take the triangle as the ratio E1 over 200 millimeter is equal to negative E2 over 80 millimeter. Negative sounds a little bit weird in this triangle, but let me just write still in the negative to make sure that we understand that it is reduced. Okay, the length is reduced. So E1 is negative 2.5 E2. Okay, and then we also know that both E1 and E2 we can describe in these relations, right? So basically we are going to substitute into all this formula, okay? Oh, E is just 1, I think. And the area also the same, right? I think we can do some simplifications. What else? L is the same, right? Yeah, L the same. E2, the difference is only the F2. To simplify, we can take maybe just L over A E. So 250 divided by 45. And divide by 200,000. So this will be 0.027 millimeter over kilonewton. And then the thermal will be 12. It's going to be negative 0.150 millimeter. Okay. I think based on this, we can describe so 0.027 F1 minus 0.150 millimeter plus, okay, E2 will be F2, or F2 is 2.5 F1 multiply with 0.027 and then minus 0.50. And this will be equal to 0. Okay, equal 0 means that when one is elongated, the materials 2 is reduced in the similar way what we did before. So the total will be 0. So the total will be 0. I hope you can get the idea from I directly write this. This is supposed to be this one, okay, plus this one equals 0. So I put all directly ready computed. Okay. Oh wait. I think.
It should be 2.5.
Yeah. Multiply, right? Maybe let me write with the symbols first, okay, to make sure that we are clear. So let me write F1 L A E plus alpha L delta T plus the E2 is 25 multiply L A E 2.5 F1 and then plus alpha L. So F1, you can take that . 2.5 6.25. So this will be 5. Yeah, I think you can check that out. Okay. This is supposed to 3.5 multiply 12 . Okay. 1027 plus 2.8 2.6 kilonewton, and F2 is 2.5 multiplied 2.6. This is 6.7 kilonewton. And then you can get the stresses. Let me write here. Stresses is from F1A and then F2A. I think you can get easily. And then for the angle here, we can get the angle theta is equal to the tangent theta is equal to E1 over 200 millimeter. And the answer, just to remind you, sometimes we forget what will be here. This is in the radian. Okay. And then the E1 can get from here. Okay, not really complete, but I think we have all the information we need. Okay. And then the angle also we can construct if it is positive or negative, means it's going here or here. If positive is the well, it depends on your assumption at the beginning. Which one is positive? If that is the opposite one, then it will be, for example, if you describe the clockwise positive, when your answer is negative, it means that the angle will be counterclockwise. Okay, yeah, I think this kind of questions, what do you think on the time? How much time you need? From the previous question and this questions, around your answer will determine how the exam will be. Do you think this type of questions worthy 40 minutes or more? 45?
45 should be
45. Or is that not sure? You can try it again at home. How fast you can try this one. How about the previous one? The previous one should be not that complicated as the one after. This one, 35, 40. I think the next one is need longer, right? Because of we need at least two diagrams, right? Diagrams for the force and diagram for the angle, right? So we need two. This one 35, okay or no? Because I still adjust the question, like how will be the question? Is it 3 questions, 4 questions? Around 3 or 4. Around 3 or 4. If 4 means that not as complex as this one, but if 3, maybe one of them will be a little bit complex, and the other 2 maybe you can write faster. Do you think 30 minutes or 35 for this one? Or still not sure? Okay. Yep. Maybe this is 40. The next one is 45 or 50. I think that will be safe, right? 50, 40. So I think 2 hours will be for the total question should be enough. It should be enough. I think I will be preparing probably 3 questions. Probably 2.